Okay, and welcome back to another SMPS story. Yeah, we have a SMPS here on the bench, which we have to repair. But since switching mode power supplies are still mysterious to many of us, we will look a little bit deeper into the design differences. I mean, we only can efficiently repair a switching mode power supply if we really know what we have in front of us. And since the SMPS are different in design, the first what we have to do is to do the analysis, what kind of circuitry we have in front of us. And so we need to understand a little bit more what different concepts are on the market. So that is what we will look into, and of course we will do the repair. We try to find, of course, the fault of the SMPS we have here on the bench, and we are going to do some experiments that you understand a little bit better how that all works together. As I said, it is a little bit difficult to do repairs on switching mode power supplies, but with some tricks and hints and a little bit more analysis, you will be able to do those repairs as well. So let's go right onto the bench. Alright, so we have here our switching mode power supply called Schaltnetzteil, so that is a German brand, as you can see. And it is produced by Electro-Automatic, EA. And yeah, you see here Harrow Electronic, which is a distributor. So it is branded for this distributor, but in general it is Electro-Automatic, which is a very well-known brand for high quality power supplies. And normally they are doing stuff for industry or professional electronics, so that is indeed a very good brand and a very good design. And this one is really a nice one, so you can see it is a 13.5 22 amp power supply, which is a right power supply for 100 watt transceivers, for instance. And the really nice thing here on this power supply is that it does not have a fan, which is really convenient because you do not have still the background noise in your shack or whatever you're doing with a power supply like this. It is very silent, and that is really great. Alright, my power analyzer is connected, and that means we have line power connected to our power supply. And additional to that, our electronic load is connected to our power supply as well. First of all, we can easily check for the voltage, which is at the output terminals, and secondly, of course, if it is working, we can load it and see if it will collapse or if it is really able to deliver the 22 amps which is promised. Okay, so let's give it a try. So we have here the LED, which is indicating if there is an output voltage present at the terminals, which are backside. And let's try what will happening if we switch it on. Absolutely nothing, and I do not see a voltage either on my electronic load, or I do not see a wattage on my power analyzer. What I should see if the power supply is drawing any power, but there is definitely nothing, so it is definitely dead. Okay, so that means we have to crack it open, and let's directly do it, and then we can go ahead. Okay, and here we have the design. First of all, we have two stickers here, and the stickers here are telling us when the product was tested after production, and that is the 22th of February 95. So you see this power supply is already a little bit older, but anyways, it is still a very nice and straightforward design. But maybe that some of you are already a little bit shocked by all the components we see here on the board, and especially if we go down here, so we see this little board here vertical in the or on the PCB, on the main PCB, and that is a controller unit. And we see here two transformers, and well, I believe that this here is the main transformer to get at least our 13.5 volt whatever. And what you may already see is that compared to the size of this power supply, the main transformer is really small, right? Remember, we are talking about 22 amps output power. And remember, in the past, if you had a linear power supply and you was looking for something 20 amps, that meant or still means that you really have a huge output or power transformer. So that is already one of the important differences between a switching mode power supply and a linear power supply. And that has already been discussed in my video 79. So that was a Flyback Converter, which we have analyzed here in this video. And in video 80 we discuss the protection circuit of the Flyback Converter in video 79. So that is already maybe a very nice information. And the design, as I already said, was a Flyback Converter. And now you already hear that okay, Flyback Converter, if there is a Flyback Converter, maybe there is a different concept. Yes, and it is. So that is the reason why we want to look into that a little bit more. And having said that, is the design we have here on the bench, is it also a Flyback Converter or is it something different? Anyways, we have a lot of components, so control circuitry and switching circuitry, and you see we have really a huge heat sink, but there is no fan, which is really nice, as I already said. And here is another little transformer, and back here is a transformer. So, you know, that is really something we need to know before we start troubleshooting. And you see, it is really confusing what we have here all on the board, and without knowing nothing, you have definitely no chance to repair a power supply like this. And there is another threat which is coming with power supplies, with switching mode power supplies. You getting very, very seldom schematics and service manuals. So you have a very complex circuit on one hand, and on the other hand you do not have a circuitry, a schematic which will guide you a little bit through a circuit like this, and that makes it even more complicated. Okay, so where would you start? So that is here definitely the question. I mean, the first, what we definitely could do, and that is, yeah, it is always the first check. So you see we have a fuse down there, and of course, so that is 6.3 amp fuse, and of course, that is something what we check first, and then of course we check if our DC is present behind our rectifier. The rectifier is below this little heatsink, so that is what I've already identified. But after that, it is a little bit critical. But we are lucky, especially here for our video. I was able to get a schematic for this power supply, and thus it is more easy to explain a little bit the design and to give you the hints you need to do your own troubleshooting on power supplies like this here. Okay, and if you've seen my video 79, you already know the differences between a linear power supply, so let me say the more old-fashioned one, and a modern power supply, a switching mode power supply. And yeah, as we have also already seen, one of the most important differences is size and weight of switching mode power supplies. So you have seen really the little transformer, the little main transformer we have already seen here in our design, and that is very important. Yeah, the size and the weight, but as well switching mode power supplies, and that is already telling us the word switching mode. So these power supplies are switching with a very high frequency compared to our 50 or 60 hertz line power. So this switching mode power supply is working with 50 up to 100 kilohertz. And for you to understand it a little bit more, as higher the switching frequency is, as lower or smaller transformers are needed. And that is the reason why we see such a little or small or tiny power transformer, because of the higher switching frequency compared to our line frequency, which is in North America 60 hertz, and in Europe and I guess rest of the world 230 volt with 50 hertz. Right. Okay, but that all does not really help. All that what I've said does not really help to understand what's going on here. It is still very much confusing, and yeah, you see here a MOSFET, and you see down or where is it? We have here a MOSFET, we have here a MOSFET, and we have the transformer here, and you see we have here an operational amplifier and a thyristor over here, and more complicated it gets if we see this board here, or this panel. Yeah, it is in German, Regler Modul means that is the controller. And when we go down here to our circuit down there, we have our controller, and you see that already is a very complex circuit, and that means even having this schematic does not automatically help to understand how it works, and I guess because of that it is the right time to go a little bit more into the detail of the different concepts, and I promise you will then be able to understand it much better. Switching mode power supplies. Why do we have such complicated power supplies where we had this nice linear power supplies which were so easy? And well, it is quite easy. It is always minimum about 2 points, and that is costs, so that means price, and it means design, and we are talking about weight and size. So that is always what it is all about. So if we have, for instance, a consumer electronic device, of course the manufacturer are looking for a power supply which is cheap if they have to implement it, and you know they have, because no design and no electronic circuit would work without a power supply. So they need a power supply, and thus they were always looking for a cheap solution. And of course, remember, when we were working with linear power supplies, the power supplies were huge and they were heavy. And that is not the only problem. There is another problem, which means again cost, because such big power supplies, transformers, net transformers we had to use, had a lot of copper inside, which is expensive. And it was clear that manufacturers were looking for another solution, a cheaper solution. And that was when switching mode power supplies came in. Well, for all purposes we need 4, maximum 5 different designs, and that are the most common designs we use. And you see here some pictures where you already see where those power supplies are needed for. But as I said, let's go right into the different designs. We only have 4 which we need to distinguish, and we need to analyze to be more successful for repairs. So let's go right into that. Right, let's start with the Flyback Converter, and that is a design we already have seen in my video 79. So if you need more information about the Flyback Converter, you are right with my video 79. And the important thing is, and how to distinguish it, is we have one transistor, which can be, of course, a FET or a normal bipolar transistor. So that is all out in the field, but you have one transistor. And this kind of switching mode power supplies, the Flyback converters, are useful for up to 300 watt. Examples where those power supplies are used are television, personal computers, printers, radios, so consumer electronics up to 300 watt. And that is the reason why we very often see this design. And of course, what we see here is only the switching part, so if you like, the high power part, but that is the part where we can distinguish the different designs. Okay? So important, once again, Flyback Converter, 1 transistor, transformer, rectifier, output. And of course, here in front we have our rectifier, our line power rectifier, because all these power supplies work with line power. Line power gets rectified, we have a filter capacity, and then we are already here at that point. Okay? Maybe for a short moment we go back to our schematic from the power supply we have here on the bench, and when we zoom in here a little bit, you see here we have our line, so L1, N and PE, that is line, and you see here filtering, that is especially for radio interference suppression, which we need for all this SMPS, because we are working with 50 up to 100 kilohertz. And then of course we have our rectifier, so a bridge rectifier, and of course we are rectifying the main, so the line voltage. So that means we have here then our filter capacitors. And remember, if we are rectifying our line voltage and we have our filter capacitors, we will have really high DC between here our plus and minus of our filter capacitor. And be careful, we are talking about 325, 330 volt RMS, and we will prove it when we go back to our repair on the bench. So here we will have 330 approximately volt DC, and then you see we are going here with our rectified line voltage to our transformer. So, and we start to analyze our circuitry which we have on our PCB by using only the switching part, because that is where we see the difference. And you see here we have 2 transistors, okay? And that means this design can't be a Flyback converter, okay? So let's go back to our another foil. Okay, so I hope now it is a little bit more clear at what point we are here in our circuitry. So once again, it is a switching part, and the switching part tells us the circuit design we are talking about. So, and our second design is a single transistor forward converter. Okay, so it is exactly the same like our Flyback converter. So we have only, so it is not exactly the same, it is working a little bit different, but it also has only one transistor, and that is what you can see here. So we have one transistor, and the difference is we need a special transformer. So you see we have here 3 windings, and here we have only 2. So that is the difference, and we have here, you know, a diode, and that is very important to our single transistor forward converter, since we need to remember that when the switching transistor gets switched off, we have a lot of energy in our transformer. And of course, if you easily switch off our transistor, so the transistor becomes high ohm, so it is not conductive here on our current line, and that means the energy is completely stored here in our transformer, and not to jeopardize here our circuitry, we need to get the energy away, and therefore we have snubber circuits, and one of those snubber circuit is the third winding here on that core, together with this diode, and therefore the energy can get pulled down by having this extra winding on the core. And you may already ask, hey, why do I use this design when when I have the flyback converter, which is much easier to build, and we do not need this third winding on our core? And that is true, but, and here is the thing, you see, this design is good for 300 watt, up to 300 watt, but if you need more power, you need a different design, and one design to deliver up to 1 kilowatt is our single transistor forward converter. And therefore, yeah, the design becomes more complicated, it becomes more expensive, you need a more or a different transformer, and therefore it is a different design. But you see, this different design was especially this design also in consumer electronics. So we need to know that this design is in the market as well as our flyback converter. One word to the snubber circuit. Of course, here we have energy in our coil as well, in the core, when the transistor gets switched off. And here you get already a hint what the circuit, our controller circuit, will deliver to our transistor. So that is a square wave switching on and switching off, because you know all the transistors which we have here are nothing else but a switch, so they are used as a switch. So very easy. If it is switched in, so it is low resistance, and all the current can flow over the transistor, which has only, if it is switched on, very low resistance, and if it is switched off, it has high resistance. So that is what it is all about, and therefore you need to have a snubber circuit as well with your flyback converter, and as well with your single transistor forward converter. Different is only higher power. And so we go along. So our third design is a 2-transistor forward converter. So you see, we have a second variant of our forward converter, and here that was our single transistor forward converter, and here we have our 2-transistor forward converter. And you see the difference again is that of course now we have two transistors, all right, and we have again a more simple transformer like we have it with our Flyback converter, but we are using two transistors, and this design is good up to several 100 watts. Maybe you can also go up to 1 kilowatt, but it depends. And now you have to decide by your development department which one is cheaper in production, so that means bill of material. So is it more cheap to have a design with a more complex transformer, or is it cheaper to have two transistors? So that is something which needs to get decided in development. So it may be that you have for up to 1 kilowatt you see a single transistor forward converter or a two transistor forward converter. The special thing with the two transistor forward converter is that both transistors gets switched equally. So both gets switched on at the same time, and that means that our 300 what have we 30 volt or 325, whatever the line voltage may be, both transistors get switched in, so that means low resistor, and you see that the current can flow through the first transistor, through our transformer, and back to the second transistor to ground. And then the circuitry get switched off. So again, we need a snubber circuit to get the energy out of our core. But basically this is a little bit different design to our single transistor, and it is more simple. And today, most of the time, it is better for your bill of material to use a two transistor forward converter, because most of the time a second transistor is cheaper than having a more complex transformer. So I have more often seen a two transistor forward converter than the single transistor forward converter. But it depends. It depends on what might be better for size and of course for bill of material. So you may see both if we are talking about up to 1 kilowatt. Alright, so we go ahead, and we are already at our fourth design variant, and what we have here is a very often seen design, and we see it very often in our power supplies, especially for radio purposes, and in general for consumer electronic purposes, because this is a design, the half bridge push-pull converter is a design which can handle several kilowatts. So you see, in comparison to our two transistor forward converter or our single transistor forward converter, the half bridge push-pull converter can really handle several kilowatts, and that is the reason why this design is so important for consumer electronic in general, but also for many industry designs. So we really see half bridge push-pull converter very often, and if you are able to distinguish a half bridge push-pull converter from a 2-transistor forward converter, then that is very helpful for your troubleshooting. I mean, you do not need to design those circuities, so that is very easy then only to distinguish what is the design we have to repair, and then you have an idea how to approach your testing, right? So that is all what it is about. We need to know where we start testing, what are we going to probe, where do we look for on the PCB, and therefore it is very important. And the most important difference for us to distinguish is that we have always two electrolytic capacitors in series, and the difference between the 2-transistor forward converter is that you only have here the normal filter capacitor, which we have here as well. So that is a filter capacitor behind our rectifier or bridge rectifier, okay? And then we have two capacitors which are the same size, and yeah, so they have maybe 400 something microfarad, and so they are equal in values. And that means if you have this both C1 and C2 in series, our line voltage, our rectified and filtered line voltage, get divided in half. So you have always half of our input voltage, our UI, which is input voltage, is divided in half. So if we have 300 volt, that means that we have here 150 volt. And here is the thing. Here we have heard with the 2-transistor forward converter that both transistors get switched equally at the same time, switched on, switched off. The half-bridge push-pull converter is different. So both transistors get switched independently. So maybe first T1 and then T2, and then again with a little pause in between T1, T2. And how that works, we have to look a little bit more in depth. Okay, half-bridge design. So we said we have divided our input voltage in two halves. So we have 150 volt on C1 and we have 150 volt on C2. So that means here positive 150 if you like, and negative 150, and here positive 150, and here negative 150. So maybe let us start with T2. Let's assume that T2 gets switched in, so that means switch is closed, and that means that the resistance here of this transistor is low. And that means that here from the positive side of our C2 we get a current flow through our core, through our coil, and this is closed, or better said high resistance, so nothing happens here at T1 again. So our current flow is here over our coil and over T2 to ground, and that means that is our first half what we did. And then this transistor will get switched off, so it becomes high resistance, and after a short while this transistor gets switched in, and we have basically the same way. So positive C1 over our T1 over our coil to the negative side of C1. And that is the second half wave we have then here at our output. So with one switching event we create one half wave on our secondary side to create both half waves of our switching event, or of our alternating current of our AC, because we are transforming. I mean, that is clear. We only can transform AC with a transformer. You can't transfer or transform DC. So that is very important. So that means the DC, what we get in, needs to get converted into a kind of AC, and that is what we are doing with our switching. But again, what have we seen? When we start here with our T2, you see our current flow starts here, and that is here not the upper side, it is here the downside of our transformer coil. So current flows here in this side, in this direction, into our coil, and then goes, if you like, to the negative side of C2. And when we look again to our T1, okay, you see that the current flow, if you would put arrows here on the current flow, our flow goes from the upper side inside our coil, okay? So our arrow would be that way, okay? And goes to the negative side. Again, if we go here from C2 through our coil, we come, if you like, from the other side. So that means we work our coil from two directions. Remember, we always have the same positive voltage here at our side. I mean, even if it is divided in two halves, we have always positive, 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 right? So there is no negative side. But on our secondary side, if you remember what a sinus looks like, so it would be something like this, okay? So that is what we know a sinus for. And that means we have a positive half and we have a negative half. I think that should be clear to anybody. But since we do not have a negative side here, so we have only positive and ground, if you like. Therefore, we must use another trick. And the trick is that we engage here our coil from two different directions. Here in our example, we only have one direction. So always our flow is always in one direction through the coil. Okay? And we directly convert the complete signal to the other side. But our half-bridge converter uses a trick that we split our DC in half, and then we have the independent switching from two transistors, and we have two different directions where we have our current flow. I hope that is clear. I know that is a little bit difficult, but just take this picture, press hold on the video, and do your own thinking about that. And if you exactly follow what I've shown you, you might be getting a bit more clear about what is happening here. Okay, so we only transfer always one half wave, if you like, to the secondary side. One transistor, one switching, one half wave. Second transistor kicks in, second half wave, because we are engaging our transformer from two different sides, and that's the trick. Yeah, now I have repeat myself 3 or 4 times. That is something what I always got criticized on, but this is maybe for the first time a little bit difficult to understand. So hopefully you can forgive that I've repeated myself 3 or 4 times. Stop the video, do it for yourself, and you may understand the concept of the half-bridge SMPS design. And we are almost ready. I believe that you and I will 95% and maybe even more see these 4 designs. So that is more than 95% I have seen are done with one of these designs. But maybe there is one more which we should know, and that is beside our half-bridge push-pull converter is our push-pull converter, so the full bridge design. The push-pull converter, so that is a full bridge design, is capable to handle many kilowatts. And that is the reason why we have on one hand this design, and on the other hand it is the reason why we do not see this design in our equipment so often. But anyways, you should be aware on this design as well, and it works a little bit like we have seen it with our 2 transistor forward converter, because 2 transistors always kicks in, and that means we see first of all maybe going through the coil, and then here back to ground. So that is the first we see, and that is because it is full bridge. We are doing the same as we did with a half bridge. We are always transmitting. Can we say transmitting one half way, or converting, or I don't know, transmitting one half wave to the secondary side of our design with one switching, and that is basically very similar to what we have seen here with our half bridge. Once again, if we switch here this transistor and this transistor, so this both transistors maybe kick in first, and you see over our transformer, over this transistor, and follow the current arrows. Is it pronounced right? Arrow? I hope so. So that is how we have our first half wave, and now the second half wave is exactly the same. Now these both transistors are kicking in, these both are switched off, and now follow the current flow through this transistor. Then we are coming here from our downside of the coil back upwards, and then going to ground by this transistor. Okay, so we have always then this transistor kicking in, or this and this, and we are doing the same with like with a half bridge. We are converting always one half wave to our secondary side. And so that is basically all we really need to know to analyze our circuitry, which we will find in the power supplies we have to fix. And our colleagues who are mostly working on televisions or DC or DVD players, camcorders, or what have we, will find for, I believe, 90% the flyback converter. So that is very common, and we in ham radio and maybe marine radios or whatever, we will find flyback converters and two transistor forward converters and half bridge push-pull converters. We find very seldom, maybe 10% single transistor forward converter. I've seen it really very, very rare. And for when I'm talking about our products, I've never seen a full bridge SMPS. I've seen it, and I've worked on full bridge converters for sure, but not, as far as I can remember, I've not worked on a full bridge design for ham radio purposes, but maybe you have worked on such a power supply. Let us know it in the comments. So I believe, once again, 3 designs you should know. You should be able to analyze, you should know the differences, and then you know how to start troubleshooting. Whew, that was a lot. And you know what? Before we really start troubleshooting here on our power supply, we should stop this video, otherwise it really gets too long. And you have seen that is already a lot of stuff. You need a little bit time to think about it, and if you really go through the different designs, you will be able to analyze it. And of course, when we start troubleshooting here our design, we have to look into our schematic. And yeah, if you go back in the video, you can watch our schematic, and maybe you already can tell in the comments what design you see in the power supply we have to work on, and maybe you already can give some hints how we could start troubleshooting. I mean, if you know the design, you should already get an idea how we can approach our troubleshooting, and that is you know, the purpose of what we have done here. knowing how to troubleshoot, how to start troubleshooting, where to troubleshoot, and yeah, to you know, you have to analyze the results of your probing. If you not able to analyze the result of your probing, you do not know where you have to look for the fault. Okay, so that means we stop this video here. Once again, I guess it is really a lot of stuff. And I think we really need 2 additional videos, because what we have not talking about is when we go here down to our power supply. Do you remember what this little PCB, this vertical PCB was for? Right, so that is the controller circuit, and that is definitely something we have to look into if we really want to troubleshoot power supplies like this. And after we have analyzed the design of our power supply, we need to know a little bit about the controller unit, because without knowing how the controller works in general, you are still not able to really troubleshoot this kind of power supply. So I guess the next what we are doing is looking into the controller circuit a little bit more in detail, and when we have finished our controller circuit, the next then will be finally fixing here our switching mode power supply. So that means we stop, as I already said. Thanks for watching, and especially if you are still here and yeah, listening to the final words of this video. So thanks for watching, and catch you next time.